What's going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. Not the physics classroom, the physics classroom. And today, we're going to talk about rotational kinematic graphs. So we've been recently talking about rotational kinematics equations and how those things might work, and how they compare to linear kinematic equations, and how we can bridge the mathematics between the two motions when rolling is happening, or when I'm talking about linear speed of a point around a rotating object and these kinds of things. But similarly to the equations being very, very closely related to linear and rotational kinematics, graphing is actually very, very similar when it comes to rotational and linear kinematics. So today I'm going to work us through just a couple example problems of how we might use our understanding of kinematic graphs to help us with our our rotational kinematic graphs. So behind me is an example problem, and it's kind of tough to see. Maybe you can or cannot see it. So I'll make sure I read the question out loud and I'll bring it to you. But most importantly, we see there's a graph right here. Okay? And this graph right here is in radians per second and seconds. And so it's hard to definitely see this, but this is our angular speed over here, and this is time over here. So this is an angular speed and time function where there's clearly changing angular speeds, okay? And so the first question we have being asked over here is to describe the rotational motion of a tire over each time interval. So I see three time intervals. I see from 0 to 1 second, I see this interval, and then, 0 to 2 seconds, and then I see a time interval from 2 to 3.5 seconds, and then a third time interval all the way over here from 3.5 to 5 seconds. So I'm going to have my calculator with me, as should you, because we're going to be doing some calculations, I assume, with this graph. Now, if we think back about our kinematic graphs, we had the idea that slope, just as an aside, the slope of this, the slope of a VT graph, the slope was acceleration, and the area of that graph was displacement. That's what we were able to do with a VT graph. In keeping with this trend of similarities, that means that with an omega time graph, our slope should be and is angular acceleration, and our area for that graph is going to be change in angular displacement, or change in theta. These are things to remember that we learned earlier on, and it just makes good sense that these relationships still hold true because their mathematical relationships still hold true. Therefore, their graphical relationships still hold true because the equations come from this graphical data. So as I think about what's happening over interval 1, I can see that this object starts at rest because its angular velocity is 0. And it begins to speed up in the negative direction. So that's probably clockwise. So it's speeding up clockwise because generally speaking, we say that things that move clockwise are negative and things that move counterclockwise are positive. That's just our convention here in physics. It's not right or wrong, but that's typically the direction that we go with. And then over our second time interval, there is no change in our speed, so it is moving at a constant angular velocity. And then we have, actually I kind of see two intervals, right? I see this interval here where there's clearly a positive slope, a positive acceleration, so it's changing direction. If it's moving forward in the negative direction, but the acceleration is in the positive direction, this tire is slowing down to a stop. So it slows to a stop as it approaches 0 radians per second. And then over this last half second interval right here, we see it speeds up in the positive direction. Probably in the counterclockwise direction now. So I see definitely three different chunks, three different accelerations, but I see kind of four varying things that are happening. Right? Speeding up, moving backwards, constant velocity, slowing to a stop, and then speeding up in the positive direction. We can explain three accelerations, or we can explain it in terms of omega. This is what's happening at each of these intervals. Question 2 wants me to now analyze the graph. So I'm going to go ahead and erase these notes. Hopefully you have these down or you understand what this graph is saying because it is an angular velocity and time graph. So I'm going to go ahead and erase these notes now so I can analyze and really kind of mark up my graph. Still an omega time graph. This says it needs me to determine the angular displacement. So basically it's asking what is change in theta from 0 to 5 seconds. That's from here to here, the entire graph. Roughly how many full revolutions is this? And then y is using t equals 5 seconds. It asks me a question later. We'll get to that later, okay? But if I remember, and I go back to my thought process in my beginning notes, if I want to find change in theta, I better find the area of this function. So I can do one of three things. I'm going to separate this thing out into some easy geometric shapes. I see a triangle underneath this part of the function, and I see a negative triangle here, I see a rectangle here, and I see a negative triangle here. Remember, when we are solving for area, it's the area bound by the function itself, which is here, and the x-axis, or in this case, it's the time axis. These are the shapes I'm looking for. So I see a trapezoid, feel free to use a trapezoid formula. I see another triangle in the positive quadrant, go ahead and use that. So as I think about this, I've got my first area, which is going to be -4, 1/2, triangle. -4 times -2, that's -8, 1/2 of that. So the first section is going to be a -4 radians. That's what that first section is. The second section has a wider, a 1.5 length base and a -4. So -4, 1.5 is going to be -6. So I get -6 radians here. This is this base here is 2, 3.5, right? Every 2 squares is 1, so I see 1, 2, 3 squares wide. 1.5 is this base. -4 is this height. 1.5 times 4 is -6 radians. This last triangle here is over a 1 second interval, still with a height of -4. So I'm going to end up with -2 radians over here. So completely in the backward direction, I have got -12 radians in the negative direction. And this little slice right there has a base of 1/2 of a second and a height of 2 seconds. That's going to end up being 2 times 1/2 times 1/2. That's going to end up being 0.5 radians in the positive direction. So when I add these two things together, I end up with 11.5 or -11.5 radians. And that's going to be my total angle swept. 11.5 radians is the area bound by this function from 0 to 5. It asks me then, not just radians, it asks me right here, how many revolutions is that? So can I get this thing over into revolutions? Well, I know there are 2 pi radians in 1 revolution. So I go ahead and I divide 11.5 by 2 pi. So let's go ahead and do that. 11.5 over 2 pi. 11.5 divided by 2 pi. And I end up with 1.83. So it's almost 2 revolutions, but I get 1.83 total revolutions based on this motion map of the graph, of this tire. Okay? Lastly, it asks me why I just can't use a typical kinematic equation. Why can't I just say initial velocity is 0, final velocity is +2, and time is 5? Well, the answer to this question is that there's a changing acceleration here. So just using a kinematic equation to describe all of this motion will not work because I do not have a constant acceleration. And we know that our kinematic equations only work if acceleration is constant. Could I use 4 kinematic or 3 kinematic equations? Sure. I could use a kinematic equation for this portion, for this portion, and for this portion, but I would need 3 kinematic equations for the 3 different accelerations taking place in this motion. So I've answered my first 2 questions now. Let's go ahead and erase these answers. Hopefully we're on the same page with this. And let's see what's up next, okay? Let's see if it's going to have us graph anything. All right, down here, it's going to have me graph what my position, this is my theta in time graph, and this over here is my alpha time graph. It's going to actually have me graph these two things as well. So what I'm going to do is I'm going to kind of over to the side sketch what I remember my omega time graph like, because I can't get them both on here at the same time. So it was like this. It was something like this, and each inflection point, this was at 2 seconds, this was at 3.5, or so this was at 4.5 seconds right here. And then let me double check. I think it went all the way to 5.5. But that was at 3.5 and then over to 5. 3.5 was here. And then this over here was 5 point. No, this is 5 total seconds. Okay, so these are the different points on my graph. So now let's go ahead and try to sketch these things out. I prefer to start with acceleration. Me personally, I think it's easiest to look at this graph over here and go to acceleration first, because acceleration is just the slope and these have constant slopes. So let's look. Over the first time interval, which is 0 to 2 seconds, I have a slope. It's a negative slope, and that negative slope comes right off the graph. It goes from over 2 seconds, it goes down 4. So that slope is going to end up being -2. So what is, I'll go every 2. We'll call this 1, we'll call this 2. Over these 2 seconds, I have a slope, or an acceleration, of -2, because that is the slope of my graph. The slope of this graph tells me angular acceleration. If the slope is -2, then that's -2. Over this next interval from 2 to 3.5 seconds, there is no slope on my velocity and time graph. Therefore, we're not going to see any acceleration. There is no change in angular velocity. So there is no acceleration. That's quite literally the definition of acceleration, is a change in angular velocity. Lastly, we go from 3.5 all the way up to +2. So we have this changing velocity from -4 radians per second all the way up to +2 radians per second in a time interval of 1.5 seconds. So let's see what that is. I'm no mathematician, but let's go 6 radians per second in 1.5 seconds. What do we get from there? It's not 6, it's a little less than 6. Is it not? Is it 6 divided by 1.5? Some of you are screaming at your cameras right now. It's 4. We have a +4. So we'll go 2, oh no, my axes are way off. It's going to be somewhere way up here at +4, all the way from 3.5 seconds to 5 seconds. I'm seeing the 3 different accelerations mapped right on this grid here. That's our first one. I think that's the easier of the 2 to graph, because I'm simply looking at the slope to come over here. The trickier of the 2, I think, it has always been going from our velocity over to our angular displacement. So we'll take a look at that one now. If I look, I go back earlier on, we talked about what's happening at each of these locations, and we talked about moving backwards, going at a constant speed, and then coming to a stop, moving forward. We're going to do this one, and I'm going to use a little less precision in terms of numbers, right? I'm not going to have the exact numbers here because I don't exactly know what's taking place. So I'm going to assume I start from 0 here. Let's start from a position of 0, and let's move backward. And as we move backward, we're actually speeding up. So we're not just moving backward at a constant rate, we're moving backwards and speeding up from a slow velocity. So again, the slope of this graph, of my theta time graph, is going to be equal to whatever's going on in my omega time graph. So I start with a slope of 0 because I'm not moving. So I'm not moving, I'm not changing my position over time initially, but as time goes on, I start to change my position more and more and more. So I had this downward opening parabola all the way to 2 seconds. I'm speeding up, Once I reach 2 seconds, now I'm still moving, this tire is moving backwards with a constant speed for 1.5 seconds. Okay? I'm going to make this open a little bit slower so I have enough space to continue my graph. Something like this, okay? Then, from 2 to 3.5 seconds, I see that there's a constant, and try and continue my constant function here to here. I see myself changing velocity, and then I have a constant velocity for this 1.5 second interval. So it's a little opening concave down from 0. Then we level ourselves out to have a constant slope from 2 to 3.5. And then lastly, as I start to go from 3.5 over to 4.5 seconds, what I see is I'm actually slowing down again. this slope is getting this graph is getting closer and closer to 0 radians per second. That means I'm actually coming to a stop in the negative direction. So we're going to see ourselves look like we're doing something along these lines, where I'm actually coming to a stop. My change in position is coming to a stop. I'm moving quickly, and then I'm moving slowly. Pretty sharp. Right? It's a pretty sharp slope here. All right? And then lastly, what do? I turn around and start moving forward, increasing my speed. So we see an inflection point curving up for the last bit of it. Okay, so this is what this graph looks like, and we can break it down, go back to what we said was happening, and now match it to this graph. What did we do? We started from rest, and we sped up in the negative direction. Then we moved at a constant velocity backwards until we slowed down to a stop, turned around, and started moving backwards. Folks, it matches my theta time graph exactly. So this is hopefully a blast from the past. Hopefully it's something that you remember and have done before. It's the same thought process that we've had during our Unit 1 kinematics graphing. If you've got questions, obviously, drop it in the comments or send me an email. But I think that this is something that is reasonable. It's just time to bring it up, dust off these skills we had from first semester. The kinematics graphs are coming back here with rotation. Okay? That's all I've got. Until next time, see ya!